We tend to walk outside, look at the ground, and assume the earth beneath our feet is completely static. But in certain parts of the world, that flat, stable dirt is actually a fragile lid covering an immense pocket of pressurized heat. Standard volcanoes appear as towering mountain peaks leaking bright red lava. A supervolcano is different. Standing inside one often feels like standing in a wide, ordinary valley. That sunken depression is called a caldera. It forms when a truly massive subterranean chamber of magma empties so rapidly that the land above it simply collapses inward, leaving a giant scar hidden in plain sight. The most lethal geological hazards on Earth are sprawling subterranean systems that hide in plain sight, directly beneath our feet. This chart shows the Volcanic Explosivity Index. To reach the highest classification, the scale of a VEI 8, an eruption must eject at least 1,000 cubic kilometers of rock, ash, and pumice. That is enough physical material to bury an entire country. Fortunately, the Earth houses only a few dozen known systems capable of hitting that terrifying threshold. Yellowstone National Park is one of the most famous. Its sweeping landscapes, vibrant hot springs, and millions of annual visitors sit directly on top of a highly active caldera. Across the Atlantic, in Italy, we find Campi Flegrei. It is a sprawling active caldera that directly borders the coastal city of Naples, placing millions of people right on the edge of the immediate blast radius. These specific locations act as the planet's most potent pressure valves. If one of them detonates, it can level the surrounding region in an instant, with almost zero warning. If a caldera the size of Yellowstone were to detonate today, the immediate physical blast would instantly vaporize thousands of square miles. A supersonic shockwave of superheated gas and rock would scour the surrounding landscape entirely bare. But the ground-level destruction is highly localized. The secondary mechanism involves millions of tons of pulverized rock and aerosolized sulfur propelling upward, injecting straight into the stratosphere. Once in the upper atmosphere, high-altitude winds catch these sulfur aerosols and microscopic glass shards. Because they sit high above the rain clouds, they don't wash out. Instead, they rapidly disperse, wrapping the globe. This creates a highly reflective shroud. Sunlight bounces off the sulfur dioxide particles back into space, starving the surface of solar radiation and cooling the global temperature. The colossal explosion at ground zero is entirely a localized trigger. The actual threat to human civilization is the resulting global winter and the severe, sudden agricultural collapse that follows in the darkness. We know exactly how this plays out because 74,000 years ago, the Toba supervolcano erupted in what is now Indonesia. Today, it leaves behind this massive lake sitting inside a crater over 60 miles long. Geochemical evidence suggests the Toba eruption plunged the Earth into a severe volcanic winter lasting up to a decade. Plant life withered in the cold, and the food chain collapsed. This chart illustrates a severe genetic bottleneck. When Toba erupted, early human populations plummeted to between 3,000 to 10,000 breeding individuals. That tiny group carried the blueprint for every human alive today, filtering our immense diversity through this narrow historical window. Subterranean pressure has the power to prune the branches of human evolution, dictating the genetic destiny of every person alive today. If you read pop science articles, you might see claims that Yellowstone is mathematically overdue for another catastrophic eruption. According to modern geologists, this is entirely a myth. Volcanoes do not operate on a predictable clockwork schedule. Magma chambers take hundreds of thousands of years to fill, and true VEI 8 eruptions are exceptionally rare statistical anomalies, not scheduled appointments. Volcanologists monitoring these sites today are focused on much smaller, more frequent events. Highly pressurized pockets of subterranean water can flash boil and create sudden hydrothermal explosions, hurling rock and boiling water at nearby tourists. Fixating on a cinematic global apocalypse distracts us from the localized, entirely realistic geological hazards that park rangers and scientists have to manage every single day. But let's assume a magma chamber does begin to show signs of a catastrophic buildup. Does modern civilization have the tools to intervene and stop a supervolcano from detonating? Researchers at institutions like NASA have explored theoretical solutions. One concept involves drilling deep down into the edges of the magma chamber and circulating cold water through the rock, effectively bleeding the immense heat away over thousands of years. Actually pulling that off would require drilling deeper than humans ever have, entirely without fracturing the chamber and accidentally triggering the exact eruption we are trying to prevent. It would also cost trillions of dollars. Geologic history is filled with violent events that pushed early hominids to the absolute edge of survival. Today, armed with a deep understanding of thermodynamics and planetary engineering, we have the ability to observe, measure, and potentially disarm the engines beneath our feet.